In this problem, I've taken two boards and leaned them up against each other. It looks like I also have them attached by a hinge just so they won't accidentally fall apart. And these things are stabilized with a string connected at their centers of mass. So you can imagine what would happen if the string wasn't there. I'm assuming the floor is smooth here. And if that string wasn't there, the whole thing would just collapse. These two ends would slide out. The left one would shoot out to the left, the right one to the right, and the center would just slam straight down into the ground. So the question here is, what's the tension in that string? All right, one of the things I need to clarify, and this is going to come in handy later, is that the forces the boards exert on each other at this top hinge have to be exactly horizontal. And the reason why is that I have perfect symmetry in this problem. So if the left board exerted a force upward on the right board, that would mean the right one exerted a force downward on the left board, and the symmetry would be broken. So the only way for them to have this perfect symmetry is to exert just a purely horizontal force. So that's going to be handy towards the end. Now our main work here is just to do a torque analysis, just static equilibrium problem. And I don't want to think about the force exerted at the top. So I'm going to go ahead and take my rotation axis right there. Now the force exerted at that little connection exerts no torque, so I don't have to worry about it. So one cool thing about the symmetry is that I only have to do half the problem. So I'm going to get the forces in just to the left half. So there's N. I'm going to go ahead and try to label angles as I go. And so I want to point something out. If I draw a vertical from that hinge at the top, it cuts the angle exactly in half. And I get an angle of theta over 2 right there. Okay, so I can see that this angle for my normal force is also theta over 2. Now I'm going to get the force of gravity in on the center of mass. So there's mg. And I can see that this angle is also theta over 2. So when I get a perpendicular component for mg, it's going to be an mg sine theta over 2. The tension should be in here also. And it's pulling this way. And here the angles get a little trickier. One option is to say that this angle right here is 90 minus theta over 2. And there are identities for sine and cosine that allow you to deal with it that way. My preference, however, is to just diagram until I can find another theta over 2. Okay, so the standard argument goes like this. This angle right here must be 90 minus theta over 2. But that angle and this angle add up to 90 degrees. So I'll just call this angle question mark for a second. Question mark plus 90 minus theta over 2 equals 90 degrees. That means question mark is the same as theta over 2. So we'll go ahead and throw that in there. That angle is theta over 2, which means to find the perpendicular component of the tension, I'm going to use t cosine of theta over 2. All right, looks like it's about time to add up the torques. So the sum of all the torques about that rotation axis that I chose up here must be 0. That means the counterclockwise torques have to add up to the same number as all the clockwise torques. And so I look at all the stuff acting counterclockwise with respect to that green rotation axis. And T would certainly rotate it counterclockwise. So would mg. There's a component of it pushing counterclockwise. So I'm going to have T cosine theta over 2 acting through a lever arm of L over 2 plus an mg sine theta over 2 acting through a lever arm of L over 2. And then all my clockwise stuff, that's the normal force. So I'm going to have normal force sine of theta over 2 acting through the entire lever arm L. So the L's will cancel out of this. And we end up with our first useful equation. Looks like I forgot a 1/2 on that t cosine theta over 2 term. All right, so if we could eliminate n, if we could find n in terms of other stuff, I think we'd be all set. We'd be able to solve for t in terms of all the known quantities here. So how am I going to get that done? N is a vertical force, so I'm going to do a vertical force analysis. And here's where it comes in handy to realize that the forces exerted, here's where it comes in handy to realize that the forces these boards exert on each other at the top are purely horizontal. They're not going to enter this equation. And so this is really fast. My only vertical forces are N up and mg down, and that means N is equal to mg. And I can plug that into this equation. and start working on isolating t. So I'm going to go ahead and subtract the 1/2 mg sine theta over 2 term while I'm at it. N is mg. I'm going to plug that in. And I end up with mg sine theta over 2 minus half of that same thing, mg sine theta over 2. Well, that simplifies to 1/2 mg sine theta over 2. And I can cancel my 1/2s and divide by cosine theta over 2, and I'll have t. So that's an mg tangent theta over 2. So there's my general solution. Let's find out what the value of tension is when we plug in all the numbers we are given. So the mass of each of these was 10 kilograms. G is 9.8. And theta was 50, so theta over 2 is 25. And when I plug that into a calculator, I get 45.7 newtons for the tension.